Hello, I'm Simon Jones. I'm part of the robotics program here at CU, and I did my final project in neural networks on neural control barrier functions. I'm just going to get started by explaining what those are, and the goal of this project is also to explore which hyperparameters work well for finding these neural control barrier functions. And also, there's one aim that we have, which is to see how well the analytical gradient that we get from a neural network can help us find these neural CBFs faster in ways that numerical solvers couldn't. So let's get started. A control barrier function is a function that gives us a validation on a dynamical system. And here you can see this is a dynamical system. We have our state. The rate of change of our state is given by the sum of two functions, and one of them is multiplied by an input. And we're going to leave this very general because it's supposed to be general. It can be applied to nonlinear or linear systems. And the control barrier function gives us a guarantee that if we start in a safe set, we remain in that safe set. And over here, this plot on the right, you can see this ellipse shape is what one of those safe sets might look like, where if you start in it, you stay in it once you have a valid control barrier function. So the conditions to satisfy what a control barrier function really is are right here, where it needs to be greater than 0 inside the safe set or equal to 0. And it has to be less than 0 outside the safe set. So this seems pretty straightforward, but then we add one more condition where the gradient of the control barrier function with respect to its input plus some special function that has certain properties of that control barrier function has to be greater than or equal to 0. So we now have a condition on the gradient, which is a hard thing to satisfy, especially when you have a numerical solution. This is why we're looking at neural networks, because they have the unique property that although they're kind of fuzzily calculated, we can get an analytical gradient in O of 1 time, and it's not dependent on anything else other than the weights and the activations. So what we do is we place a grid of initial conditions on our dynamical system, and we plot them and say, okay, I want to learn how much the constraint is violated if I start in a certain place on my grid. So we have this 2D grid in this case, and we say, let's learn how far out I go into this red area. And we generate a bunch of training data, split it 80-20, and we do that and test it with a combination of 9 different hyperparameters where we have 3 different losses and 3 different activations. We have Huber, log cosh, and mean absolute error for loss, and then Tanch, Gelu, and Alu for activation functions. And all these activation functions are differentiable, which is really important for our case. So you can see here the ones with arrows are the highest performers in terms of test accuracy. And this is a histogram showing where the error lies for all of the test samples. And oddly enough, 3 of these are Huber loss, and we're kind of seeing that it's independent of activation. The first 2 are Tanch activation, so there might be something to be said about Tanch activations. But from what I can see so far, is Huber loss seems to perform the best for a loss metric when training. And you can see that when we plot the loss versus epoch, it converges to 0 within the first few hundred epochs, which you would think that means it's overfitting, but it's not. So obviously we're seeing really good results with Huber loss when learning these control barrier functions. When I plug it back into my solver, which I won't go into those details because it's not relevant to this class, you can see that it drives the trajectory. If it starts inside of the safe set, it drives it to the origin using this neural control barrier function, whereas the unsafe input that we were given previously is this blue line that leads us way outside of our constraint and violates it. So our control barrier function does indeed drive us to be safe. For more information, you can scan this QR code to see the manuscript, which is a work in progress. But yeah, from this point on, the future work might be adding constraints to what input so that the CBF input doesn't just drive it as hard as it can to get inside the safe set. That would be more optimization focused. Or we could also look at verifying the robustness of the CBF right here to say, well, it's a neural network. How do we verify that it remains within a certain set? So this is all future work. Yeah, so thank you for listening. And for my acknowledgements, I'd just like to acknowledge my PI, Marco Nicotra. He's the head of our lab, and you can contact me with my email down here or visit my website if you'd like. Have a good day.